Get started. Today, like I said, we're going to do this last day on RD. We're going to be thinking about basically what we talked about last time was kind of like, what if everything works out smoothly in your RD approach? It was kind of like, here's a checklist with the implicit assumption of like everything you're going to check off on the list is going to work correctly, in the sense that you're going to show the RD works well, that there's no issues with imbalance, that there's no problems with bunching. You have a continuous variable, et cetera, et cetera. And so today I'm going to talk about a couple of the things that are kind of different, like the hiccups that you'd basically run into, and what are basically things you can do for that. And I think over the course of that, I'm going to kind of try and walk through like functionally, what does some of this stuff look like in practice? Because it's a little more challenging. And then I'm briefly at the end going to talk about regression kink design, which something like the theory behind it is actually sort of challenging and complicated, but I kind of more want to just highlight it to you all so you can see what it is. And it, I think, should be really straightforward, just looking at the examples. Happy to chat about it more at the end, but this is a relatively new thing. And we'll talk about it at the end. Okay. So we're going to do a little bit of warm up to get to kind of the first issue that we run into, which is really, we talked a lot about this estimator and kind of the properties and how you do it. We talked a lot about the estimator itself, but we didn't really get into the specifics on the asymptotic distribution of the estimator. Like we didn't talk about the statistics of it. And, the only real piece that I talked to you about, right? So this is this sharp RD version, right? We're taking the limit from the right and the limit from the left, and we're taking the difference between these two. This is how we define this. And I've kind of been hammering you all with this idea of the trade-off between a large and small bandwidth on each side of it, right? So the small bandwidth, the idea was, well, you have low bias, but it's very noisy. The big bandwidth, it's biased, but there's less noise. That's kind of, if you take one thing away from the estimation procedure for RD, that's hopefully one of them. Of course, one of the things that's complicated is that all the asymptotic arguments that we make, for the most part, there are some exceptions to this, are made as the bandwidth shrinks, right? So this idea of, well, everything's made at one point anyway. So these are all approximations to a given point in the first place. So what does it mean to pick a big bandwidth or a small bandwidth? Well, these are all like finite sample things that we need to keep in mind. And so this question is like, how fast should the bandwidth shrink? Another way of saying that is just like, how big should the bandwidth be relative to our sample size, right? That's really the trade. When we're going to be talking about this size of the bandwidth, we're really talking about like, we have X number of observations and we have this data, running variable. How big should we make the bandwidth as a function of the sample size? And so there's this useful result this is actually Canonical et al. Have this really nice write-up, which is kind of like practitioner's guide to RD. So if you want more stuff on this, I put in the syllabus. It's definitely worth looking at. But kind of the main point that they make, this is kind of the decomposition that's worth looking at, is, think about the mean squared error of an estimate of our estimator. So this is the sharp RD estimator. It kind of has two pieces, right? So any mean squared error, hopefully you remember this, there's mean squared error can always be decomposed into the bias squared of the estimator and the variance of said estimator. This is like in machine learning, the trade-off is always between, a little bit of bias in order to really reduce your variance. We talked about this when we were doing shrinkage. All these same ideas apply. And so what you can do is you can talk about the bias and the variance here. You can do an approximation. This is not actually an exact statement, but it's an approximation, a first order approximation, where you can talk about what the bias is of these sharp RD estimators and what the variance is, where it's going to be a function of a couple different things. So one thing it'll be a function of is the polynomial of how you do your estimator. So this is kind of redundant the way I wrote it, but P is the polynomial degree of your local regression, right? Your local regression estimator. So for example, we've been talking about local linear regression, the idea that we're fitting a local line, but one could easily imagine fitting a local quadratic, right? These are not exclusive. You could do a local cubic, etc. So the degree of that polynomial is going to be a function, is basically, so P is equal to 1 if you're linear. This script B is the leading bias term of an expansion about the bias. We'll talk about that in just a second. And then this script V is the variance of the estimator. So these are basically using, I think they're called Edgeworth expansions to think about the approximation to this function, the distribution of this function. So I think the analogy here is like a Taylor expansion, right? So it's a Taylor expansion of what this estimator looks like. And so we're going to get into that. We're doing a lot of details on this just so you can understand intuitively what the different pieces are. So what a lot of times that's chosen for the bandwidth is the thing that minimizes this term. So fix P, fix the kernel, and do local P regression. Well, what H should you choose? Well, there is an H that minimizes it, and it's a function of the variance, and it's a function of the bias, and a function of the sample size. So when P is equal to 1, then it's on the order of n to the minus 1/5. So this is a pretty common number here. And the key idea is that the bandwidth, this is exactly what we talked about, right? Is like, as the variance of it goes up, the bandwidth is going to go up, and vice versa for the bias. The one thing that I just want to say is what this bias, the only thing that is of consequence that I want to just highlight, because it's going to come back when we talk about these things in practice, is this bias term, this leading bias term. And we're going to have to draw a picture for this. Just turn on. Okay. I'll turn it off automatically. Let me make sure I can do this. So here. So you guys don't need to learn about fixed income. Oh my God, my dog is sitting right in front of the board. Sorry, I'm going to be weird about this so that I don't move him. Okay, so all I want to just highlight is what the bias term is. So this is kind of the canonical example. So here's our running variable. An easy way to think about this is that what we have is a function that looks like, this. It goes like that. And the idea is that it goes up like this, and then it's like this. So we have some jump here we're interested in, right? And obviously, if we have a big bandwidth, so say we picked a bandwidth here between, oh, this pen sucks. That's right, I threw this away last time. From here to here, and we fit a line, it's going to be really a pretty crappy line, right? It's going to look like this. Actually, I'll do it in the magenta. It'll look like this, right? So there'll be serious bias relative to, this will be our bias term here, right? And so the idea and the reason for that, the reason the line sucks is that a line is a bad approximation of a curved function when you're doing it over a long space. So if we let that get small, then the line would become better and better. And we would get a line that looks like this. And we'd be much closer, right? Obviously, I made it perfect here. Does everybody see this okay? It's all right? Okay. You know what so I'm just gonna stop the show for a second so that it's big enough so you guys can see it. So in this, so like I said, when you have a big bandwidth, the line is small. When you have a small bandwidth, the bias is smaller. When you're going to think about what the bias is, the literal bias in this script B I was talking about. So there's a script B term that I'm worried about. There's two pieces of it, which are going to come from the bias that's on the left and the bias that's on the right, right? So when I'm thinking about the bias in estimating this difference, it's a function of B plus and of B minus. The point is that I can think about each of these individual bias terms as being a function of how bad an approximation my line is on the left or on the right. So the first order term in my bias on the left is going to be, so ignore this green one for a second. Well, if I think about the quadratic term of this function here, the quadratic term looks like this over that space, right? So it looks like basically like this. And what I can think about is the relative difference here, the bias that I'm getting, the first, basically the second order bias, or the first order bias that shows up in the bias term is coming from the derivative, basically the second derivative of this function. All this is to say is that the first term in this bias component is coming from the second derivative of your actual underlying conditional mean function, which is to say that if I knew what that was, if I knew what the second derivative was, I'd be able to approximate what this bias was. This is going to matter for when we think about doing how to actually approximate this bias. Okay, so hopefully that's clear so far. This is all kind of cool. It's like, this is like non-parametric. This is just what non-parametric estimation is. So we talked about there's these things, bias isn't known inherently, but that's a component of it. The point is that we have this term. If you pick this bandwidth, you are going to be picking something that shrinks at a rate of n to the 1 over 5, n to the 1/5. So now, if we do that, basically the point is that if we choose that bandwidth, then one of the kind of key points is that it doesn't lead to zero bias in our distribution. So this is this result that's kind of that is known in this literature, is that if you pick the mean squared error minimizing bandwidth, that's not basically, that's doing too much smoothing. It's basically picking too wide of a bandwidth, such that you are, relatively speaking, having too much bias, such that you have basically a bias term in your asymptotic distribution for your estimator. So like if I write it literally, the formulation for this, if I write it down, is the idea that my tau hat minus the true, don't worry, I'll move it back to my thing. I don't know why I bothered. That this is the point is that this is no longer normally distributed mean zero, but rather that you have to account for some bias term here, that this is normally distributed with mean. So typically there wouldn't be this additional adjustment term. You would just want this. But what it's saying is that if you do it at that rate, you have to adjust for another additional term. And the reason that matters is, so why you have to account for the bias term? Like, why is it that I didn't just like move that thing over? Is remember that I'm always, when I'm thinking about these distributions, I'm always scaling by root n. And so if I have a bias term in there, I'm like, it's not like it's just like shift the distribution. It means it blows up this whole thing because it's off. It means that you're not consistent. And so you don't have this nice asymptotic distribution around your test statistic, around the true value of your bias. And it's not a consistent estimator, more importantly. So what does that mean other than being like interesting econometrically? Well, typically, what you can do is well, okay, so the first point that I just want to emphasize is, remember, this is all like an approximation. So, we're talking about like n to the 1/5 versus n to the 2/5. Like, who cares? Like, these are just these are relatively small differences. They're kind of rules of thumb. But the thought experiment basically kind of highlights like how much you need to focus on being very close to the bandwidth versus relatively far away, and how much can you choose the optimal bandwidth. And the reason this matters, and we'll get into this, is that historically there was a bit of a logical incoherency of how people did this. They would choose the mean squared error optimal bandwidth, and then they would pretend as if there was no bias when they did the inference. So like, they both can't be the right thing to do. You need to either do something smaller than the mean squared error efficient bandwidth, and then you can assume that it's normally distributed, or you have to adjust for the bias in some way. One notable thing, and I think this relates to a question that got asked maybe it was last week when we first did this. You're thinking about variance, like heteroscedasticity on one side of the cutoff or the other, and thinking about that. So one thing that's interesting to think about here, so that's not an issue for this estimator. But when you're thinking about efficiency, I think, Rosie, this was your question, is like thinking about efficiency. If you want to pick good bandwidths, what you could envision is that the variance is much larger on one side. And so what you might need to do then is you pick a bigger bandwidth on one side of the cutoff than in another, because, right, you need more data to kind of account for the fact that it's noisier. And so you're going to adjust accordingly. And so this basically, all you do is you just allow for two cutoffs. They're easily defined on each side. And this is very natural. And almost all the packages we'll talk about, this comes up automatically. So let's talk about the ways that you can do this. So there's kind of two ways in practice. So I was kind of alluding to this idea of you pick a smaller bandwidth otherwise. So what that's called is called undersmoothing. So what you could do is you can pick a bandwidth that is smaller than the optimal one to undersmooth, which what that means is you're basically going to have more noise. You want more variance. You're allowing for more variance such that your bias goes to zero. That's called oversmoothing. Undersmoothing. What they're advocating for, so Canonical, for those of you who don't know this, so Canonical, Cataneo, and Tediunic have a bunch of papers. So if you aren't kind of familiar with this space, I'm going to point you to the packages that they have. It's like they have staked out this territory in this way that's kind of amazing. I mean, they have so many papers, and sort of Cataneo is kind of on all of them, as is Tediunic, and they sort of have written a lot on this topic. And they were really they did a combination of things. One, they wrote these papers that I'm just going to talk about. And two, they've provided a huge amount of statistical software for Stata and R that let you do these things. And so it's kind of the default approach for almost everyone in most of these. But what they advocate for is, rather than this thing about picking a smaller bandwidth, is they say, what you should do is you should do the MSE optimal bandwidth, do what we talked about, and then directly account for the bias. So adjust for the bias in your estimate. And the way that you're going to do that, going back to our picture, is what you're going to say is, all right, well, look, you can do local linear regression. Also do local quadratic regression. Like, you could just do the same thing, but re-estimate it, do it in an optimal way, and find out what the quadratic function looks like. Then, using that quadratic estimate, you can get the derivative there and you can say, pretend that's true. That's the true function. That gives me an estimate of what the second derivative is for the function at the cutoff, right? It's a plug-in estimate, and I can directly estimate what the bias term is. So it's going to give me an estimate of the bias for the linear estimate that I can directly plug in. And obviously, so the key part of this assumption in this paper by Canonical and co-authors is that bias plug-in estimator obviously has to converge to the true bias. And so under certain regularity assumptions, it does. But this is really cool, because now you're saying, look, I can account for this, and I'm going to use that to adjust the bias, and I'm going to also show you how to do this for inference. Canonical, Cataneo, and Farrell have this JASA article where what they do is they say that you can do this to correctly do inference, that is, get the right confidence intervals, and it's actually going to be better than the undersmoothing approach. And the reason for that is that doing the MSE optimal bandwidth is so effective, and the bias adjustment is usually pretty accurate, such that it's much better than kind of an ad hoc way of trying to do undersmoothing and using the other approach. So what I want to do, I'm going to show you exactly what I mean in practice in here, but are there any conceptual questions here? Like, where I'm kind of giving you the theoretical background so that I'll be totally honest with you. We're going to like walk through the output of what one of these looks like. This program, prior to like me really spending time understanding this paper, is like very confusing to understand what's going on. So now hopefully we can kind of like read this and be like, oh, we know exactly what the pieces are of this. So this is the RD robust package in R. So I am doing that Lee paper. This is for that Lee paper, the 2008 one that we've been looking at so far. So I'm literally estimating the effect of the incumbency on the vote share subsequently. So I want to literally go through every piece of it to kind of highlight what these map to and what we've been talking about so far. So the first one is this bandwidth type. So how this bandwidth type command here is, how did you choose the bandwidth? So there are other choices, but this one is kind of the default, and it's this mean squared optimal one. So you picked your bandwidth to be mean squared optimal. And right, so that hopefully that makes sense. The kernel, how did you choose, what's your kernel that you chose? So here it's triangular. Triangular in RD robust is default. My understanding is that triangular kernel has nice property at the edges when you're doing, so RD regression is always trying to estimate something at the edge of a function. And I think triangular kernels have nice properties there. My preference is kind of do uniform because it's very transparent of like how it works. You're running a regression on X number of observations, but this is the default. It seems totally reasonable to trust them. Effective number of observations. So there's the number of observations that you should understand. Effective number ones is how many observations are within the bandwidth. The order est p and order bias q. So that's, what's the polynomial order, and then what's the thing that it needs to be at least more than, like, what did you use to fit the bias? So you can make it bigger than 2, but you need at least 2. You need at least a quadratic. H and B are the bandwidths chosen, and you see it's on the left and on the right, for the functions on, so the H is the main estimate that I'm doing, right? It's just my local linear regression. So that's the bandwidth for it, and it's the same on both sides. I didn't allow it to vary for both. And then B is the bandwidth for the bias estimator. It usually needs more data because it's a quadratic. And so you just do the same exercise. It's a mean squared optimal choice as well. And that's how you're going to get, that's why, so these ones are going to be slightly bigger here. That's the 2 of them. This row term, I'll be honest, I don't totally follow it. Basically, the relative size of this is going, like the closer to 1 this is, the less bias there is usually. I think like the better that this of an approximation it is. I wouldn't worry about this row term. And then unique observations is like the number of mass points. So the idea being like, if it's discrete, right? So maybe you have many observations, but then you only have 10 points on the running variable. There's just a bunch of unique points. There's only a few unique points. And so that would show up here. Okay. So that's all these things. Now let's talk about what's going on here. So there's kind of there's 3 things to keep in your mind. They only put 2 here, but I'm going to show you the 3 in just a second. So remember how I told you first, what you could say is, forget about the bias. I'm going to use this bandwidth, and I'm just going to pretend there's no bias. Like, who cares? You're econometricians can't tell me what to do. So that's what they call the conventional approach. So you're going to have a conventional estimate So first you have an estimate. That's what the coefficient is, which is literally your estimate. You'll have a standard error associated with that. That'll be your variance. This estimate is basically the same thing as if you ran a regression yourself on both sides of it. So you could run a regression with that bandwidth chosen and do kind of an interaction and set it up, and that would get you exactly these terms. And then you have a z statistic, the p-value, and your 95% confidence interval. Yeah? So robust basically accounts for the bias in two ways. So first, there's the bias in the point estimate. So there's the thing that you're testing around when you construct your confidence interval. So remember I wrote that thing down here where I was saying there's that B term that you have to adjust for. So like, you get some point estimate, you're going to get 5.876. When we do stuff and we don't have bias, our confidence intervals are always centered around that because the normal distribution is symmetric, right? So if it's symmetric, then you'll do 1.96 times your standard error on one side, 1.96 times your standard error on the other side, and you're done. When you do the bias adjustment, you adjust for the bias, so you'll recenter it around kind of the right part. Then you'll do the symmetric thing around that. That's in the recentering component. Then there's also this aspect, and this is what shows up in the Canonical, Cataneo, and Farrell paper, is that you want to account for the additional noise of the estimation of the bias term. So for that, the point is that this bias estimate is noisy. If you don't pay attention to that and you treat it as known, right? You've estimated it from the data. So there's statistical uncertainty associated with that. And so that's going to increase your variance of your overall estimate. And so this robust thing is accounting for that estimation of the bias term. So what it's doing is they're reporting that confidence interval around recentered and using that more robust variance estimator. Now, there are kind of two steps in here where really what you could do is there's the bias corrected estimator. And then, so if you look at this, so this is usually the output of it looks like this. But if you do this all option, you can see all of the three estimates. So there's the conventional one I just told you. There's bias corrected, which gets you the coefficient and adjusts for the bias. So the bias is around 0.3 here. The standard error is the same under the bias corrected one because you're ignoring the impact of bias on your variance. And so the point is you get this confidence interval around the recentered estimate. The robust allows for the recentering, and it has a bigger variance term because of this uncertainty. So that is all to say, I want you to kind of understand all the pieces, because what's confusing about this package is it just like gives you a crap load of different things. And then you're like, well, which estimate am I supposed to use? So what the Cataneo et al. Sort of handbook is advocating for is basically you should report the conventional coefficient estimate. So that coefficient estimate is the right one to report. Basically, the reason for this is that it's more efficient from a mean squared error standpoint than the bias corrected estimator. And so the claim is that you should you should do that, but you should report the robust confidence interval. That's why they report it this way. They say, take the 5.876, but then report the confidence interval 2.53 and 8.55. So the thing that I want you to be able to remember, if you guys like end up doing this, it's not going to be centered around 5.876, right? It's centered around the bias adjustment. So this is always a little bit weird, and I don't want you to sort of write a paper and then somebody says, well, why is that not centered? Why is that not in the middle of a distribution? And it's because the confidence interval basically is accounting for that in the recentering. Okay, any questions on that? This is like the thing that everyone's going to use more or less to do this. if you have a continuous one. So I'm going to advocate for if you don't have a continuous running variable, there's a different package you should use. But in the continuous case, it would look like this. Okay, great. So what do we do if we can't shrink our, and the thing to say about this is like, I know I'm like advocating for like writing your own code. You should really be using just one of their packages for doing this. I mean, they like did all this work. I mean, maybe if you're a Python person, I would just use the call package from Python to call their thing into Python from R, like just call R from Python. There's just like no reason to reinvent the wheel on this. They've done such a good job of like laying the groundwork on it. There's some stuff that's more complicated later, but this is just so naturally falls out for much of what they're doing that I see no reason to not just use this. Okay. So now we're going to kind of get into what shows up for me a lot in the work that I've done, which is like, what do we do if we can't shrink our bandwidth? So the whole point was like, well, these things are a function of, we have continuous variables, but like the idea is as we got more and more data, this is essentially identification at a continuous point. But what if the way that the data is sampled, or if just the way that it works is discrete? So age is a good example here, or it's basically, so this is from a Phil Oriopoulos paper. So it's like, what if the running variable is basically discrete? So in this example, to just give you a case of this, although my own work has this too, is this is basically looking at the impact of a compulsory schooling age law in the UK, where the idea is basically the law, there was a big law change in compulsory schooling. And so if you basically turned 14 late enough, you would have been forced to take on more schooling. And if it was earlier, you would have had less schooling. And so the idea is that this line here is when you're testing for this discontinuity. But the point is that it's really a function of year. So the running variable is in year and the data is measured in these years rather than having like something that's continuous. And so I think this is this extremely nice paper by Michael Kolesar and Christoph Roth in the AER that discuss exactly how to deal with this. And what they propose is basically this honest RD estimation approach, which is going to approximate the bias that you get by using this discrete running variable by assuming a maximum second derivative. So basically tries to account for this fact that you're going to have to interpolate pretty much no matter what. So, Kolesar and Roth say, all right, forget about this. We just had this whole debate about bias adjustment versus undersmoothing. They say, forget about that. That's like fine and good. But like when you're in the continuous case, you always have this trade-off at least. Like you can get closer than the mean squared error optimal one. You can undersmooth more and just ignore this issue. And then it's always appropriate to just use the standard Ecker-Huber-White, so like the robust standard errors. But the point is that this argument only really works if you can get enough observations close to the cutoff. And with discrete variables, it basically fails. So what's happening there, right, is that you're extrapolating this conditional mean function to the cutoff. And so what's happening, if we go back and look at a picture here, is that let's take now, instead of these functions, so now imagine we have a discrete running variable. So we have, 1, 2, 3, 4, right? So it's discrete. And we have these points here. So it's going to be a very similar looking function to before, but now we just have points. We have some cutoff. Here's our cutoff. And it jumps up like this. So all I've done now is I've just binned what our function looked like before. Hopefully this kind of looks familiar. I know my, here we go. So what we're going to do is, so here's our RD estimate, right? So it's kind of similar to what we were talking about before, but now we got this problem of like, well, shoot, we have like these points, but what we need is we need a point here to compare this estimate. And so the obvious thing is you'd say, all right, well, let's fit like a function, or we'd fit a function that, looks like this. And that's going to get us that point. But, if you look at this, we look at this function here, and obviously we can have more points so that we're not just extrapolating off of 2 points, right? It could be discrete, but still have more points. The issue is like, well, this is an like if we think about this is an extrapolation that's occurring, right? And it's always an extrapolation. But basically the point is that this distance here, this delta, that distance is supposed to go to 0, but it's not going to in a discrete running variable case. And so the question is that the amount of bias I could have is by how much I can get this function wrong, right? So it could be that the function looks like this or like this. It could really spray out in any kinds of directions. And so the point is that what Kolsar and Roth say is, well, if I take this, there's some maximum second derivative for this function. So they talk about a class of Holder functions, which is, I don't even know if I'm pronouncing Holder correctly, but it's a set, Holder functions, which is basically these under very particular general class of functions where what you're going to do is assume that they're bounded in some way by a maximum derivative. So, it can be a big change, but it can't be, the point is that it can't go from here all the way up to here instantaneously. Like there's some amount to which there's smoothness in it. So it's continuous, and it has at least a second derivative, and that second derivative is bounded. And the point is that what that lets you do is it lets you talk about, once you're willing to put a bound on it, well, then you know how badly you can be off, right? Like you can only be off by so much as a function. Oops. Oh man, is this pen getting bad? You can only be off by so much here, right? You could be basically this delta times the second derivative is going to put a maximum bias on how badly you can do. So what does that mean? Well, the analogy is actually kind of nice because we just spent all this time talking about what to do in the RD robust setting. Well, in this setting, what they're suggesting is that, oh, sorry, I'll put the picture back in case you wanted to see it. We can use this now to talk about what the confidence intervals should be. So this is basically, this approach is a way of you could do this with discrete or continuous running variables. But the idea is that what it's going to let you do is talk about how you should basically have to, uncertainty, you should have to allow for as a function of misspecification error, right? That's what it is effectively. The discreteness creates misspecification error in your function that's not going to go to 0. And so you're going to put a bound on how badly you can do, and that's going to give you confidence intervals that are valid under that kind of potential misspecification error. But what's nice about this, of course, is that similar to the statement that we said in the what's it called? The RD robust setting, you're still going to use the same point estimate because that one is mean squared efficient, but then you're going to report these robust RD honest confidence intervals. And let me switch this over now. So, and let me put I need to put the slides. Okay. I almost did it. So, basically there's this package, RD Honest, which is going to let you do that. And it works extremely well with these discrete random variables, running variables. And my understanding or my experience, and I've written a paper with discrete running variables and I've tried a number of things, is I have found that RD robust, I've written 2 papers with discrete random, the same discrete running variable, is that RD robust, I have found that I did not believe the results that came out of it in terms of how it chose, like it seemed to really choke on the discrete running variable issues in a big way, in a way that I was like very unhappy with. Whereas I found RD Honest has done extremely well in it. Now it has this extremely weird thing that you have to do now. It's a new tuning parameter, right? Now I told you had to worry about bandwidth, you had to worry about kernels, blah, blah, blah. Now I'm telling you also have to worry about maximum bias, because that's a thing that you have to choose as a researcher. So that can be hard to do ex ante. Armstrong and Kolesar have, basically this is the theory paper that drives the underpinnings of the Kolesar and Roth paper. Armstrong and Kolesar basically talk about ways to do this in a data-driven way, given additional assumptions. I'll be honest with you. So what I have used so far is this next paper I'm going to talk about advocates for this idea of, well, what you can do is just fit a polynomial on the kind of the global function on the left and on the right, right? You split it into 2, and then just look at what the second derivative is of that function and try some scaled version of that. So you see what the second derivative is in the data that you've seen, and then you can multiply that by 3 or by 4 and use that as a starting point. It's kind of a starting point for what your potential maximum bias is going to be. The reason that's not perfect, like you can't always do a data-driven, is that doesn't allow for some functions. Like that puts an additional restriction on the space of functions. And that's what they talk about in the paper. It's just like, being too general sometimes makes it too hard to kind of actually do these things. So the biggest thing is to really just show that your results are robust to this kind of parameter choice. Okay, so another paper in this space that I really liked, and when I was working on these papers in this space, I actually started kind of trying to work on this, but struggled to get it off the ground. But I want to highlight it for you all because A, there's some nice packages for it, and B, it can generalize to some other settings in education or in spatial RD that can be useful. We didn't really talk about spatial stuff too much, but this is as good a place as any to talk about it, is that, so this is a paper by Inbenz and Wager I want to say it's in Restat. It's either in Restat or in JBES. And what it's doing is it's a very similar approach in spirit to the Kolesar and Roth approach, namely that it's putting a bound on the second derivative. It's kind of thinking about this in an honest way. But what it's doing is it's redefining the problem in this numerical method approach rather than using this honest RD confidence interval application. There's basically just like a numerical, it does not have an analytic closed form solution, but rather it's this numerical minimization problem that they set up. That's kind of this linear optimization problem. And that makes it computationally a little bit more burdensome. That was the issue I ran into that this thing, I found that it didn't do well on my computer with a big number of data points. But what's really, so there's 2 things that are useful about it. One, it thinks about a slightly smaller class of functions relative to the Kolesar and Roth ones. And so it has slightly smaller confidence intervals, potentially. The second is that what's really good about it, in my mind, is that it generalizes very easily to multivariate RD settings. So we talked about at the very beginning, this Sandy Black application with thinking about borders. That's like in space, right? You can imagine there's a line that's delineating the border between, say, New Jersey and Pennsylvania, and you're thinking about an RD along that. That's a multivariate line potentially that varies in the X and Y coordinate space. A lot of times people will collapse that down to say distance to the border, but there's potentially lots of interesting reasons to think about why different parts of the border have different treatment effects and ways that you'd want to weight that up. Or if you thought that like there were 3 states, so you guys may not be super familiar with the borders of Pennsylvania, New Jersey, and like New York. But if you think about that, right, there's like this interesting triangular aspect, and you could think about different laws that are happening in this space and where these effects are concentrating. So there's lots of kind of interesting ways to think about treatment effects along those boundaries, and as you vary across, like weighting them up in particular ways. And so that's one of the aspects that they touch on in this paper. It also touches on this literature that's not in the spatial setting, but is thinking about multiple running variables. So this paper, this graph is on the right, is from using data from Jordan Matsudaira's paper, where he's thinking about multiple running variables, where there are treatment effects that come from cutoffs based on math scores and on reading scores. So if you're above some threshold on either math or on reading, you kind of get this treatment effect. So then so if you can see that, if we just ignore the y-axis, there's an RD across 0. Same story is for reading, there's an RD across 0. Well, now there's an interesting question of how should I think about treatment effects along this boundary? Well, because there's an effect for going across the math cutoff. There's also one for the reading cutoff. And how do I want to kind of weight up those different treatment effects? These are obviously going to be different groups of people. So they have, so this opt-RDD code works reasonably well for it. It has a little bit more computational issues because it's in this numerical optimization setting. The Cataneo crew, as I guess you could call them, the sort of the huge set of folks who have that RD robots, they also have this package called RD multi, which is allowing for this multiple cutoffs thing. So one thing, we didn't really talk about it, but I guess it's worth highlighting because if we're going to talk about literally everything in RD, we might as well cover this one too. So remember that. Remember I showed you that thing of the in Israel there that class size the size cutoff. There's basically the idea was that there are these multiple cutoffs, right? So there was some outcome here, and there were multiple cutoffs where there was a treatment. Like you could imagine it was like this, and then you saw this decline. Okay, so let's make this concrete. Sorry. And there's a decline. And then there's another jump, and it looks like, so there's, multiple discontinuities here. And when you have an experiment like that, you want to use as many of them as you can. And so the key thing is that a lot of times what people will do is they'll renormalize so that you're picking boundaries around this, and then you're renormalizing it so that these are all stacked on one another. That's a very common approach. But that has its own issues because then you're kind of reweighting things and assuming that the function looks the same across groups, right? So if you think about this, I wrote this really ugly graph, but if it looks like this, you could very easily imagine that the slope for this guy is different than the slope for this guy, right? And so if you pool them together, you're going to be weighting two different sets of functions. You're going to have bias in the way that you estimate them. Does that make sense, people? You kind of get that? So the natural thing to do would be to literally estimate each of them separately and then pool them in some efficient way, right? This is kind of almost everything that an econometrician does to sort of fix these things is they say, let's do it separately and then pool in some efficient way. So that's the idea here, is that when you have these multiple cutoffs, there are efficient ways to kind of do them separately and aggregate the data in a useful way. The key thing here too to keep in mind is that if you're doing this in a fuzzy RD setting, which is like IV, is that these are different types of treatments, right? These are basically different instruments. And so you're going to get different compliers in the different groups. And so you're going to be weighting up different treatments as well. But, go see the Cataneo crew has some code for this as well. This one I have not used, but definitely something to keep in mind. This shows up a lot in the education setting. For those of you who are interested in education, these multiple score thresholds for different types of things. This is going to come up as an issue. Okay, cool. So what about bunching? So when we talked about this last time, I said, do a McQuarrie test and hope that it works. That's not very satisfying because it's entirely plausible that it won't necessarily hold. So there's kind of, what the concern is that there's a manipulation in the running variable. So what I mentioned this before, the idea was like, look, it's a test score. If you're above some threshold, you get into some school or you pass your class, et cetera. Well, one thing you could imagine is as soon as there are economic incentives, people are going to manipulate what their test score is. There's going to be some sort of intervention that moves people from one side to the other. So this is a pretty extreme example from D and co-authors in the AEJ, where what they were looking at, I don't know if any of you are from New York State, there's something called the Regents exam in New York State, where basically, and if there is anyone from New York, correct me if I get this wrong, is basically the idea is that these are basically standardized exams that you have to pass in order to qualify for a diploma. Like these are necessary things to pass to get your high school diploma. And there are like multiple cutoffs. There's the passing threshold, and then there is the like honors threshold that matters. So 55 versus 65. And for a while, there was basically this ability for if people failed, they would get regraded by their local teacher. Basically, their own teacher would regrade things that had just been under, like they'd recheck them. And so there was a huge amount of manipulation for obvious reasons, because you basically would, you wouldn't have passed. You wouldn't get a diploma if you didn't pass this. And so as a consequence, what happened is there was this manipulation. So you can see this is a particularly egregious example where there's obviously this. And so this whole paper is kind of about changes in the system that did this and kind of what the mass points were here. But in a lot of cases, there's cases where there's some amount of difference there, where it's like less stark, but there's maybe looks a little bit different. And the other kind of flip side of this coin is that even if there is a break, you might be underpowered. It's like hard to detect these things if there's not a lot of data around these points. And maybe there's a difference in the point estimates, but the standard errors are really large in your McCrary test. So you fail to reject, but it's because you're underpowered. So there's this paper by Gerard, Ruckinen, and Roth. This is the same Roth of Kolesar and Roth. That what they do is they propose like a partial identification approach to allow for the possibility of bunching. So think of this as, how can I have an experiment? I really want to use this experiment, but it failed the McCrary test. Or I'm like worried about like it was really underpowered to test it. How can I kind of show the robustness of my results? Like how sensitive are my results to this manipulation? And so they have code as well. I will say the community of econometricians who work on RD are surprisingly good about providing code. So they have this code for R and Stata called RD bounds. It's not very good code, but it's code. I tried it out. It does work. And the key result hinges on the idea that people manipulate in one direction. So they always talk about it being rightward manipulation. So think of it like here, like people manipulating to the right because they want the treatment. It really just matters that it's one directional, like people manipulate into the treatment. So if it's leftward to get the treatment, just call it leftward in your mind. The point is that they all go in one direction. So what's going to happen is that there's going to be a set of people who are going to be manipulated to be on the other side, and that those manipulated folks are masking the true underlying effect. It's basically contamination that's coming from these rightward manipulated individuals. They're basically always manipulated onto the right side of the cutoff. They're effectively the excess mass, right? They're the people who we're not getting them like on the left or on the right. They always got put onto the right. And so we could never identify the effect for those anyway. They're not identified. And so what this paper does is it derives what are called sharp bounds. And we'll talk, if we cover partial identification, we'll talk about what sharp bounds means. But basically it means the best you can do for those who actually could be affected by the treatment. So conditional on not being one of these people who would always be manipulated over to the right, what's the effect of the cutoff? And the way that you do that is to identify the share of the masking individuals. So what share of the population are the folks who are getting moved from one side of the cutoff to the other? So it turns out, under the assumptions from this paper, which are pretty innocuous, as long as it's one-sided, that what you can do is you can say, all right, well, let's take the relative density of the forcing variable on the left and on the right. and do 1 minus that, that's the share of individuals who are mass. So this is why I say it's basically they're the excess mass. Notice basically that this number here, this tau, if the McCrary test holds, then FZ0 minus is equal to FZ0 plus. That's equal to 1. This whole thing is equal to 0. And so this number gets bigger as the relative mass on the left is smaller than the relative mass on the right, right? So in the extreme, the density on the left would be 0 and the density on the right would be 1. And then so it's everybody is manipulated over to the left. That's the extreme in which everyone is bunching. So this is really nice. This is really nice if you have bunching issues in your design. Frankly, I haven't used this before, but I think if you have a setting in which you're worried about this, this is like a very clean way to potentially test for robustness of this. And, you know, so relatively new. So this is in quantitative economics. This came out last year. I think is certainly a pretty reasonable thing, especially if you're worried about robustness. It's a nice thing to basically add to the McCrary test as a potentially useful second thing. For those of you who just said, wait, I don't know if we'll cover the partial identification part. If we do, if you've ever heard of like Lie bounds, where you think about attrition, people talk about attrition out of it, and you can use Lie bounds to kind of bound what the effect is on something. You're worried about attrition from your sample. This is a very similar kind of analogy to that, in the sense that you're figuring out who's attritting basically and scaling up and down as a function of that. Okay, last 2 things, I think I have 2 things remaining that I want to cover are the following. So one is a thing that I realized, I did it for myself for a paper, and then I realized like, this actually seems like the sort of thing that is like not obvious for someone who was working on it, and you should know how to do this. And this is going to apply in a ton of settings, but RD one is a really good one because you're doing kind of fancy things. So imagine you have an RD that you ran. So you have the effect of a test score, or you have, or some test score threshold, or, you know, like in papers I have, you have this Medicare RD where it's a threshold as a function of age, or we go back to that Oreopus example, right? Where you have what's the effect of education on, say, men versus women, or, you know, immigrant versus natives, et cetera. The question is like, say I estimate the effects for each of those groups. So I have the conditional average treatment effect for, let's just say it's for men versus for women. And I'd like to compare those 2 effects. How would you test whether or not those are different from one another? So I'll tell you, I'm not going to put anyone on the spot, but it's worth just thinking about it for a second. Like, what would you do? Say like you literally had done an RD and you reported it for men and for women. And then a referee is like, well, I want to know if those are statistically different from one another. What would you do? So what I will say is one very natural response that is a good one to inculcate in yourself, because it's like the easiest thing to always do, is you just bootstrap. That's like a lot of times, anytime somebody wants something complicated statistically, a great knee-jerk reaction is, oh, well, I'm going to bootstrap. We haven't really covered kind of what we mean by that, but and it's worth, I'll try and find some references for this, at least if we don't cover it, is bootstrapping at least allows for this concept of like resampling. You can kind of run through the estimation procedure without having to kind of know how to do any interaction between them. That's not necessary in this case though. So that's how a lot of folks, for example, when you do a really complicated estimation technique where you don't know kind of the asymptotic distribution, you'll just bootstrap it in order to be able to estimate the uncertainty, because the process is so convoluted. In this setting, you don't need to do that, in part because you kind of know asymptotic normality holds for these estimates. And so then it's really straightforward, and you're doing a really straightforward transformation. So the way to see this is kind of imagine you were just doing this in OLS, right? So if you're doing this in OLS and you're asking, well, what's the effect of some dummy on group 1 versus group 2? Well, you'd say, all right, well, let me run the regression. I have a constant. I'd have a different constant for group 2, right? So you put in a dummy for that group. You'd have the running variable here. you'd have I missed one. Sorry. You should have a running variable on the left, and then you should have the running variable on the right for each group. And then you should have the jump, right? So that would be like my sharp RD effect for the two groups. You should have the interaction. You should have the running variable for the other group, allow for a different slope. And then you'd look to see if the jump looks different between the two of these, right? This is basically saying like do an interaction, fully interact it with all of them. So I'm missing two terms in here because it's not fully interacted. This tau sharp RD diff would give you the difference in the effect for between group 1 and group 2, or group 0 and group 1. It would be the relative effect of tau. And then for group 1, the effect would be tau, this additional tau diff on top of it. If this is 0, then the effect is the same for the two groups. If it's different from 0, then they have different effects. This is basically the approach you could do if you picked a bandwidth and used the uniform kernel and you weren't worried about bias in your estimation, right? You could exactly do this and you'd be done. You would just be assuming undersmoothing. But now I've told you all these tools that you can do to do RD. You have all these fancy things like RD robust or RD honest, and you might need them in different places. And so the question is like, how could you do this difference in that setting? So basically what you're going to do is you're going to apply the delta method to this transformation. The delta method is like overkill to call it delta method, but that's the way you should think about it. So really what it is imagine you have this tau W equals 1 and tau equals W 0. So I'm going to call them tau 1 and tau 0, but it's the RD effect for group 1 and the RD effect for group 0. So for men and for women. So that we have an RD effect for men, RD effect for women. And I want to know what the difference is. Yeah? Right. That's what I asked you. Is that difference significantly different from 0? I'd like to know what the statistical distribution is of that. Well, that's a function of two parameters, tau 1 and tau 0. And if you maybe remember from suffering through last year's econometrics class, you can get any functional transformation of parameters through the delta method, where the variance of this thing is the gradient vector, the gradient derivative. It's basically the derivative of this function with respect to each parameter, transposed times sigma times the gradient vector again. And this sigma is the variance covariance matrix of tau 1 and tau 0. And so how do we get that sigma? Well, in this case, it's really easy because we estimate them separately from each other. So we know that the covariance terms are exactly 0. We just estimate one thing on one sample. We estimate another thing on another sample. They're totally independent from one another, the treatment effects. And so they have 0 covariance. And so this sigma is just the diagonal of the variance terms. And so you're going to get this product of the two. The nice thing is we can actually check our work on this. So in this example, we wanted to know the variance of the difference. Well, if we assume that they're independent, like they are, then remember the variance of the sum of two things is equal to the sum of the variances plus the covariances. And the negative comes out and is squared. So you get that the variance of the difference is just equal to the sum of the variances. And that's exactly what you get if you do the delta method here. You're going to get exactly this term here. The delta method is an exact statement in this setting. And that's just because the linear approximation for a linear function is exact. But if you have a nonlinear thing, like say you cared about the ratio, or you cared about, so I have a paper where we care about like the variance of term, like we're taking like some more complicated function, you can do that and you can do the delta method. And that lets you kind of talk generally about this. And what's cool is you can do all the estimation, you have the estimate, you get out the standard errors from your different things, you plug in, you do delta method, and you're done. And you've got exactly all the comparisons you need. You don't have to worry about doing anything complicated. What I want to highlight is that this also works with RD honest. It's sort of, in RD honest, you have to worry about these bias terms for the confidence interval. Basically, you have to go read the online appendix of this Armstrong and Kolosai paper, which has the confidence interval discussion. It's really not any more complicated than do the delta method and then take the sum of the bias terms in all the parameters and you're done. And so I hope that that is at least useful in the sense that I feel like that's a thing that is kind of non-obvious, but is a really kind of reasonable way to kind of redo this, is that there's no reason why you would run these all separately if you're going to do it. If you're going to do it group by group, and obviously you'd like to kind of hold that fixed in this setting. Any questions on that? Okay. In the last, well, it'll be less than 10 minutes. In the last couple of minutes, what I just want to highlight is talking about regression kink design. So I have never used this myself. I have read a couple of papers that have done this, and it is sort of, it's starting to show up more, and it's starting to show up more in part because there's more administrative data sets. But actually, for the purposes, this is a good one. I feel like this one is less obvious. So pretend DAGs are RKD. Have you seen an RKD before? Okay. All right, survey says no for the most part, except for a few lucky ones, as you might say. Not actually. So we'll talk about it, and I'll talk about what are the caveats here. There's a reason why you potentially haven't seen it before. So one is that so much of our discussion so far has centered around a discontinuous jump in the outcome, or a discontinuous jump in the treatment rather. So the idea being that there's some binary thing that turns on as you cross some threshold. And what RKD centers around is that there is a parameter that is continuous, that you cross some threshold, and that shifts the value, basically the derivative of that, not the derivative of it, basically the relationship between that outcome and the running variable. So the name is pretty provocative, but it causes a kink rather than a discontinuous jump. It can also cause a jump, but the feature that it's really highlighting about is about this kink in the relationship. So Card et al. Basically say that this initially was coined in this Nielsen et al. AJ paper, where basically what they're saying is you're exploiting a difference in the slope of the parameter rather than just a level difference. And the reason this is kind of seductive is that there are a lot of policy tools, especially in public finance, where the things that are happening are linear shifts in incentives rather than discontinuous jumps. So if you're thinking about tax schedules, or for example, unemployment insurance, for example, this is an example from Norway, I believe, where they're talking about basically UI benefits as a change with respect to earnings. And there's there's basically a kink in the relationship that happens at some cutoff. So the relationship between earnings and UI shifts at a cutoff, and you'd like to exploit that because you think of that two people on one side versus the other are potentially comparable in the same way that you think of it as in regression discontinuity. So you can kind of see here, there's this UI effect, and then you can see the effect on time to next job. This is hopefully clear that there's kind of this same idea that, well, what you have is you have this flattening here in the same way that you have with UI benefits. And so you'd like to use this kink to identify the impact of UI on time to next job. Does that make sense? So this approach is really cool. It is, seems like a very good potential approach. In the sense that for the following. So one, there seems like a lot of examples where you can potentially use it from a policy standpoint. Two, it makes sense a lot from a statistical and economic standpoint. Economists really think of people as responding to these types of kinked incentives in a big way. but the statistics of it make it kind of hard. And so the reason for that is the following, is that slope changes are just hard to detect. So, did the slope change because of curvature or did it change because of a kink? So if we look at this line, like, you have good economic reason to think that this kink exists, but you could easily draw a curve that's just a quadratic through this point and fit a line in a very easy way. Once you allow for a relatively flexible polynomial, there's no reason to think that this isn't just coming from something arbitrary. And so this Ganong and Wager paper, which I mentioned last time, is really talking about exactly a test to account for this fact, really saying like, look, we kind of have a sense of what the curvature of the function looks like, kind of what does this look like relative to other settings. And so this is a good approach to keep in mind. So, both doing this test and thinking about it, I have to say that I worry a little bit about this, that I do think that this is one of these things where I worry about there being enough power. But the sense that I've gotten is that administrative data sets are really the place where this starts to, like, if you have a data set with millions of observations, you really start to be able to pin down these conditional mean functions pretty tightly. And that gives you a pretty clean way to see this stuff. So Sasha and Darte's job market paper was trying to exploit this. And so this is a good example of where the sensitivity, it's challenging here because there's this sensitivity, but regardless, it's kind of, her job market paper is about the incentive to declare bankruptcy relative to this cutoff. And the point is that it's not so much of a jump, although there could potentially be a jump. There's really this like discontinuous impact on, basically the idea is that when you cross this threshold, more and more of your asset is seizable by the trustee. And so the further you get away, like when you're below it, everything is protected. And so there's limited incentive to file for, or there's more and more incentive to file for bankruptcy because all of your assets are protected. When you're above this, more of your assets will be seized. And so she's exploiting that discontinuity or that discontinuous change in the slope. The challenge is like, how big of a kink is it? Like you could really allow, like there's a much more statistical sensitivity is what becomes much more challenging. So unlike this, we already have this problem in the I guess I don't have any good pictures in this one of like, here you could already worried about jumps, right? This is the same problem we worried about in the discrete problem is like, well, you see some other jumps further on. And so it gets just even harder with the RKD example because slope changes are even harder to detect than jumps. Kind of the analogy is trying to think about structural breaks. Like structural breaks that are jumps are much easier to detect than structural breaks that are just slope changes. Same idea holds here. Yeah, so that's pretty much it for RD. I guess one thing I want to just say out loud, I didn't end up having time to cover, is related to this idea of thinking about external validity. There's a couple nice papers. So Josh Angris has a paper with Mika Rokkanen about this, thinking about extrapolation. And Hito Inbenz has a paper with, I want to say Morea, about external validity in these settings. Like external validity is this is like where we started, right? When we started on day one of doing RD, I said, well, it's great, except you can only estimate it right at this one point. And so then there's this serious concern of like, well, is that useful at all? I think most people who use RD would say, well, it's better than nothing. Like it's really great that we can see it in these real life examples. But the question becomes like, how useful is it in other settings? So if you're interested in kind of exploring that more, there's some stuff there. In the end, you're kind of subject to all the same constraints that you're always subject to, which is that without more assumptions, you can't do more. If you're willing to make more assumptions, then you can do more. And so it's this tension in this space. And I think probably the right way to view it is, if you're studying an interesting question, usually estimating a treatment effect is at least interesting among some subgroup. And so then the next question is like, do that first, then worry about external validity. So that's pretty much it. I will wait I'll hang out if you have any questions, and otherwise have a great weekend. And don't forget about the homework.